Hi, my name is Vikram Singh. I'm a PLM in the AI data center team, and I'm going to talk about automated congestion management in AI ML backend fabrics. So if I may draw an analogy of what we're going to present today, we're all familiar with these metering lights, and these are primarily used to manage congestion on our freeways during rush hour. Right? And the way this works is there are cameras or sensors that detect how much traffic is flowing or how much congestion is there on the main freeway, and then they change the duration of time this light is red, right? So practically how much traffic you're allowing in. If you allow too much, then it adds to the congestion and it just worsens the situation. If these lights are red for longer, then you actually are creating congestion at a different point and not utilizing the whole bandwidth available, right? So what we're trying to do is give that flexibility of fine tuning, depending on when congestion happens. So if you see, just to describe the challenge, let's put ourselves in the shoes of network admin, right? Like you're managing this backend cluster, which Praful talked about. And so there are two types of complexity, right? One is monitoring complexity. There's so many entities that you have to monitor. For example, here you see 256 GPUs. If it's a small cluster like 256 GPUs, you may have 12 switches with 64 ports each. So there are 768 ports, and then quickly you see each one can have 6 queues on each port. So you can have 5,000 plus entities that you have to monitor, right? And you may need historical view, as Jay was showing. From a provisioning complexity, there are only a few dials available to tune the congestion, and they're listed on the bottom right. But in terms of, today it's a manual process. It's tedious, it's error prone. Somehow the network admins is supposed to know what are the optimal values for this network without knowing anything, what the traffic from these machine learning workloads will come, right? So sometimes you may need to tweak, like as Praful said, you may need to tweak a certain things for a particular model. And more importantly, in a multi-tenant training network where there are either multiple jobs running and the traffic is flowing from the same fabric, by the time you get a ticket or somebody tells you, hey, my machine learning job is slow, you may not be able to recreate that other job that was interfering at that time. So you don't know what to tweak, right? So these are some of the challenges today, and that's what we're trying to solve through automation, right? So let's see how Apstra and all the things, Terraform and probes that you have seen, we can build something to solve it. So here what we have done is we've written this DCQCN auto tune app. What it does is it leverages all the things you saw, Jay showed you from the probe. So we are continuously monitoring key KPIs that tell you when congestion happens, or performance KPIs, right? And we'll do a demo soon, so you'll know. And then once we detect that, hey, I think the intended config is not doing what it's supposed to do, we make a decision, and then we do a closed loop automation. We use Terraform to actually tweak that configuration throughout your fabric, and then continue to monitor the effect of that, and until you have an optimal set of these congestion configuration, right? So this is like, there was a question, how are we creating? So in this demo, what we are doing is, this is our lab that you'll be touring shortly. And we use Ixia to generate this Rocky V2 traffic. And actually, we're generating so much traffic that it overwhelms the receiving NICs, right? So it goes through 4 leaf and spine switches. And that congestion manifests at the egress leaves. And that's where we are filling up the buffers. That's where we are applying the algorithm that I'm going to show you. So we monitor the ECN, PFC, and tail drops via Apstra, and then we basically make a decision, and then we push out this config. Now there are a few options here. You can say, hey, wherever the congestion is happening, only tweak the congestion parameters on that switch. Or as Jay showed you, Apstra has this concept of leaf and spine. So if it's happening in a leaf, you can choose like, hey, only apply on all the other leaves, because it may happen on the other leaves as well, or spine, right? So that's the thing. And also we have ServiceNow integration. So we will update everything, that all the decisions this app makes onto the ServiceNow. Right? So Praful went through this, and I'm going to go in a little bit more detail before I just show you the algorithm we are using. So as you know, DCQCN, so there are two primary mechanisms in Ethernet to control congestion, right? So the first one was PFC. This came first, and it's more of a brute force or a hammer approach. In this case, if you see the spine, the red link, if let's say that's congested, what the switch does is switch will monitor its buffer, and if it's around 90%, it's configurable. But if it's getting to a point where it will imminently, the packet drops is imminent because buffers will fill up, it sends a message pause frame to the neighboring switch downstream. And it says, hey, don't send me, stop sending me traffic for a particular amount of time, ticks for this whole priority. And the way priority works is usually the NICs will mark a DSCP value for all RDMA traffic. There is a default value for NVIDIA and others. And then what you do is you map that, you take that and map these things in a queue where you apply both these techniques, right? So eventually this pause, the other switch will get in trouble and its buffers will fill up and the pause frames reach the NICs and they stop, right? So the goal is how to make Ethernet lossless, and this is what makes it lossless. But the problem with this approach is, it doesn't have the granularity. So it will use, let's say one link is blocked, it's going to block all traffic from that priority from the neighboring switch. It has 63 other or 62 other ports where the traffic could be fine, right? So that's what is troublesome with this technique. But there is ECN. With ECN, what happens is wherever, let's say they take the same example, you have the spine, one of the interfaces is congested, and what ECN does is and you have these two knobs where you can configure. Probabilistically, it starts marking packets, right? And these are one-way flows. One GPU is trying to write some memory chunk onto another GPU's memory, and all the NICs are continuously looking for this marking. So in the DSCP bit, there is a bit that it flips. The receiver actually detects that there is congestion somewhere in the fabric, and then it sends an explicit congestion notification packet back to the sender, and then sender backs off the flow. So if it was sending at 400, it steps down to 200, and then eventually, it can. So this is more effective. It's granular. You're only impacting the flows that are impacted by a particular congested queue, and B, it actually remediates it because the flows will back down, the congestion goes away for temporarily, and so DCQCN actually is judicially using both these techniques, or sometimes they only, as Praful was saying, you can only use ECN as your primary method, and this is what is DCQCN, right? So
you mentioned that PFC causes all the traffic at that priority to stop?
Yes, from the neighboring switch. Yeah, on that interface.
Okay.
So let's see, so what we have done is, so I'm simplifying here a little bit, but this is easy to understand. What you're seeing is the x-axis here is actually the buffer occupancy in percentage, right? So whenever congestion happens, a switch is congested at some queue on some port. This is what you apply, and there are two configuration parameters, Kmin and Kmax. So for ECN, so what it does is, as buffers fill up, hit the Kmin lower watermark, they will probabilistically start marking the packet. So if let's say you are somewhere at 10%, the switch will start marking 1 in 10 packets as ECN, right? And if the ECN doesn't kick in fast enough, you keep filling the buffers, you cross Kmax, that's when all the packets in the flow, in the queue will be marked ECN. That means all the flows will be impacted, right? And then you have PFC. So sometimes, there is a function of these control packets being sent to the sender. If there is some delay in there, it may still not act fast enough. So that's when you have some PFC as insurance, just to kick in and buy some time for ECN to eventually kick in and so what we have done is, so that this is the set of value that a network admin has to know somehow automatically, like, hey, what my pattern should be. And the practice is they all shift, they start very right, because you don't want to slow unnecessary down. But with that approach, what happens is you don't have much buffer left to actually prevent drops. So what we have done here is we keep monitoring on the top right what you see, how do we adjust left. So everybody starts with a very relaxed ECN config so that all the applications can breathe. They're running at the maximum possible. Your load balancing is your first defense. But still, if congestion happens, what you do is if we keep monitoring the buffer occupancy by seeing, hey, are there any PFCs being triggered? Or is there a tail drop happening, right? So if it is happening, that indicates that your ECN is not reacting fast, and whatever config you did, we need to move a little bit left, trigger ECN sooner, so that that eventuality of dropping packets is alleviated, right? So that's how this. What we do is we make a decision, we keep moving left, and then we see what's the impact of this. If it's still PFCs are triggered or packet drops are happening, we keep moving left until the system is stable, right? And once we do that, then how do we move right is when you have avoided this boogeyman, the situation which may cause packet loss, we start saying, okay, if the buffer occupancy is between your low and high watermark, that indicates that, hey, my ECN is perfectly tuned and the round trip times for these CNPs are perfect. So let me actually allow the applications to run at higher bandwidth, breathe more, and move right. And it will help you find the most optimal value based on whatever workloads come in real time. Right?
So the metric it's trying to drive is packet drop rather than job completion time or something like that, which is a higher level metric.
So you're right. So because it doesn't have the notion, job completion time can only be measured by the application, right?
Right.
So, but if there is congestion happening, packet losses can slow that job completion time. So it's trying to avoid that by saying, hey, let me slow applications to a not a full crawl because but let me slow them down reasonably. So they're still running. That may impact that may help the job completion time rather than if packet losses happen, retransmissions are triggered.
No, I was going to just add to what Vikram said. This is an application that's running on top of Apstra with the APIs. This is one implementation we've done, but at the end, you can take it and do what you want. But you're right that there could be, if you have access to job completion time, you can absolutely make that part of the algorithm that you implement. And we're going to experiment with a bunch of things. We're going to learn along with our customers in terms of how to make this, as effective as possible. So this is just one example implementation of what you can do.
Yeah, but the application people are never going to tell the network engineer about their jobs.
No,
Yeah,
I mean,
yes.
well, I mean, no. So what we've seen in terms of the divide is that they're never going to allow us to configure anything in the application. It's kind of like the integrations we have with VMware. We don't go and implement and configure VMware. However, yes, we do get visibility into it. We get access to that telemetry.
Yeah,
but at the end, we're controlling the network.
Allow us.
Hmm?
If they deign to allow us.
if yeah.
It'll be even harder in the AML applications. Yeah. So I know you, Matthias, you had a question earlier, hey, how much drops and stuff. Once we know that, we can tweak, hey, how much drops you want, to move this further, right? We could do that. But just wanted to say that, hey, future. So this is one idea we are testing, and as we do more experiments, we are going to find more opportunities. What else can we tune? What other parameters, load balancing, other things that we will enhance this, right? And so Apstra now allows you to not only deploy, operate, but also help you fine tune some of these performance KPIs to help you run this optimally. So with that, I will let Raj do the demo. And
just to set the stage, right? Like Vikram said, we want to start. I think of packet drops as an edge, right? So you want to get away from the edge as quickly as possible. And then because the view is really nice from the edge, you want to creep closer and closer and then find the spot where you're safe, right? So that's kind of my mental image when I wrote this code. So this application, what it does is it basically uses Apstra to manage the fabric, right? Jay spoke about configlets, which is basically these config snippets that you can push out into Apstra. And Jay spoke about probes, which basically, tell you what's happening, right? So I'll just let it go. and we'll run it on 2 times the speed because we like fast. So the situation we see here is there are both ECN and PFC anomalies happening on the fabric because the XCR is pushing traffic out. Whenever we see PFCs or trail drops, we start moving left, right? And that's basically what's going to happen. And what you also see here is, because it's so much fun to see log messages. I just put everything up on ServiceNow, so it basically updates this incident ticket, right? The general idea is like we want to make the network admin's life easy, right? So with the network admin would much rather see what happened than be told something really bad happened, right? So the general idea is as it sees this application, as it sees PFCs, is going to start shifting left, basically shifting that window left, hopefully slowing the traffic down, and it keeps updating ServiceNow and says, hey man, I just dropped it down. I dropped it down some more. I dropped it down some more, and so on. And that's basically what we're seeing here. This was written while this is going on. This was written in Python using the REST API, the REST API that Jay spoke about. And you can see already that it started at 60-90. It's already gone to 40-70, right? So 2 cycles have happened, and it's already gone to 40-70, and then it went to 30-60, right? Now at this point, in a couple of seconds, it's going to notice that there are no PFCs, right? So PFCs are gone. The ECNs are gone. Like there are still ECNs. So basically, we moved far away from the edge, right? Now, we still want the applications to breathe. So we know we are close to the edge. So we start moving right now to actually find the edge, right? So we go right and we find edges, right? So it basically says, it basically knows now that if it sees PFCs again, that's the danger zone, right? If I was a singer, I'd start singing the Danger Zone song, but I'm not. Because everyone is safe. So it sees the edge now. It knows the edge is there. So it wants to find a spot where it can still breathe, but it's not going to fall over. So now it's going to start moving left slow. Like we went when we moved initially, we were moving in steps of 10. Now we're going to move in steps of 5 just to find the edge, right? So from 40-70, it went to 35-65. It moved a little bit. And at this point, I'm willing to take bets on whether it's going to stop here. I know what's going to happen, and or it's going to go further. So yeah, we have like 80 seconds for your bets. No, but the general idea is right, like because you're kind of safe here, you pause here longer so that the changes can propagate. The system can settle down for a bit, and once it settles down in a particular zone long enough, this particular application will just stop, right? It'll basically say, I think I found the safe spot, and it'll just stop at that point. It could also potentially just keep running, right? You can basically say, like, I don't see any PFCs. I've not seen any PFCs in the last minute and a half. Maybe I can move again. Maybe I can go to a better spot, right? So it can basically run in like infinite mode, not infinite, like not stopping mode, like while one, right? It can do that, or it can basically say like, I'm done. This is good. This is where I'm going to stop. So you can basically, it's basically up to you, right? That's kind of the power of Apstra. You can make your application like this whole concept did not exist like 3-4 months ago, right? And it's now a thing. And we're talking to Apstra PLM, it's going to become a thing in Apstra, right? So like that's kind of where we want to go here. Like we want to use this as a general kind of framework. Thank you, where anybody can develop their own applications with Apstra, right? This code is going to go out on GitHub like everything else, and anybody can do whatever they want. Like you want to make like config backups, make config backups. Be happy. Use our code. Be happy. That's really what we want. And as you can see, 3060, if anybody had 3060, you won. So at 3060, everything is happy, it stopped. That's 3060.
3060.
So, yeah, there's
we were right.
like, yeah, there's like, thesis quality research to be done here, to be honest, because like, we are doing something like very simple and straightforward. Like the window is only 30 wide. We move the window, like in lockstep. We could, expand or contract the window. We could expand, we could change the percentages by which these, like right now, the percentage is 0, 100, right? When you hit the window at 0, the probability is a linear probability. You could play with that. Somebody said like, can we change this based on completion time, right? Of course we can, right? See, this is a pattern, right? The pattern in which this window was moved is something. If you can match that against completion times over a period of time for different kinds of loads, you can figure out what the ideal pattern is, and then again, I wish I had a joke about learning, but I don't. But this application can be smart, right? It can do things where it knows this kind of workload would probably need this kind of window and automatically do that.
This Python application, you mean the Python,
Yeah, I just wrote Python code, man.
You're describing an ability of the software, the networking software engineer.
Yes.
Using whichever platform they prefer. You prefer Python.
Yeah.
To do all these kinds of things.
Yeah, exactly.
Yeah.
Yeah. That's what I meant.
But we would like to see is that Apstra has an AI in it that determines.
No, we don't. We don't need to see that this moment.
My question on the Python is there a good Python library for Apstra, or are we directly making REST API calls inside the Python code?
Yeah, 5.0 is coming up with like a brand new API library. I used an older version, but the latest.
I like SDKs. I'm happy with an
like
SDK than an API.
Like a really fancy SDK is coming out. So you'll have that for sure.
You didn't talk about flowlets in the optimization, but that's another potential thing that you could turn on or off based on how things are going.
Yeah.
Yes.
I mean, I don't make those decisions, but I would get some grad students for this work. They get a thesis, we get an application, everyone's happy.
But you're right. So we took the hardest problem first, congestion management in Ethernet, and then we are looking at others. And one of what you pointed out is one on our list.
Just to expand on that other question. To expand on that, there was an earlier question on SmartNICs as well. So one of the ideas that we had that we started building an app 2, let's call this app 1. App 2 is we're looking at congestion metrics on not just the switches, but we're looking at congestion metrics on the SmartNICs. If you see, for example, out of order packets on the SmartNIC as an example, then you know that your DLB is not configured properly. So you can go tweak your DLB timeout on the switches to respond to congestion that you see on the SmartNIC. So that's an app that is going to follow very soon after this app as well.
Yeah, thanks, Praful. I'd forgotten. Michael Henkel from Juniper is working on that. The next thing I'm going to do is integrate his work with this code so that we can have more smartness.